Hi, we're going to do polar area here and give you a conceptual idea. When we sweep out angle measurements, we sweep out, like for instance, I just did 0 to pi over 2. So we're sweeping out, and that idea really holds true for when we try to find the area, for instance, this petal here. Except for the radius is always going to change, and so we got to figure out where the end of that radius is. So if I look now at some of these formulas, we did rectangular coordinates. We do have this formula here for the area under the curve, and we have the little rectangles. Now we want to move to polar, alpha to beta 1/2 r squared d theta. Now where does that come from? Well, if I go over here to the area of a sector of a circle is 1/2 r squared theta. That would be the area of this thing right here. How do I get that? Well, if I do a part to whole relationship, theta to 2 pi is the same thing as the area is to pi r squared. That's the area of the whole circle. If I cross multiply and try to cancel off the pi's, what's going to happen is I'm going to be left with the area of a sector of a circle. Now, how does that help us? Well, this theta now, this little theta right here is a little piece of theta, so we call it delta theta, just like delta x. And so we want these things to get smaller and smaller, but right now we represent it with delta x. And so instead of theta, delta theta. Sorry, I said delta x. Then if I set this up, this is going to be a summation. Now if I did have a figure, I'm going to have a bunch of these little sectors. So I'm going to have 1/2 r squared delta theta, and then these little widths, or this little angle measurements, they're going to go to 0 when n goes to infinity. When that happens, big summing machine, we're going to end up with the formula that we do have for the area of a sector of a circle. Now, if I take some different ideas here, what if I wanted to find the area of r for sine theta? I need to sweep out. And in this case, I could just sweep out one piece, and that's the same as all the other pieces. So if I can find the area of this one piece, multiplied by 8, I should be good to go. Now, how do we go ahead and do that? Well, we set it up in our formula that we do know, that we just had, 0 to theta. Let me go do this first. And so now I want to give you a visual of what's happening here and why is it 0. So if I look at this, this is kind of that same piece of that petal. And I got this little laser here to show us how these little cuts go. But first of all, I start here at parallel. Parallel is going to be actually at theta equal to 0. Now I'm going to do all of these little tiny little sectors of a circle and try to find the area of all of them as I sweep around. So if I wanted to find the area of just this piece here and then multiply by 8, I could find the area for that other piece there. Now notice I go straight up here. This tangent right here is going to be pi over 2. So I'm going to be going from 0 to pi over 2. And I hope that laser little thing helps you. I find students have trouble seeing this, how this sweeps out. And so the only thing I could think of was that laser. Okay? And then that would be my r that I'm dealing with. And notice r is always changing as I go around. So to put this in my formula then, I'm going to go from 0 to pi over 2, as we just said. 0 to pi over 2. And then if I can maybe move this over, there we go. I'm going to get 1/2 r squared d theta. And remember, r is this right here. And then that's going to be one petal that I do have. So I did go from 0 to pi over 2. I didn't go 0 to pi over 4 and multiply by 8. So I'm going to multiply this 4 petals by 4. 0 to pi over 2, same exact thing as what I had up there. That's how I would find the area of the flower, the rose that I created with that polar equation. R is equal to 4 sine of 2 theta. Okay, so now we're going to try to get a little fancy and try to get the area between two curves. One of the curves is this one, and then I'm going to do another one, which would be here with the r is equal to 3. And so when I guess I'm not doing the area between the two curves, but I'm going to do the area that's enclosed in this piece. I could do the area between two curves too, and that would just be a subtraction problem. But I want to shoot out until I go, well, here, I'm doing this fancy little thing here, because I want to do the laser and show you how this sets up. And why I'm doing the laser is just because students kind of ignore that this straight line hits the rose curve all the way up to this point right here. So if I start sweeping out, I'm trying to find the area of this right here. So it's between this curve and these bottom portions. Notice I'm hitting the side here. When I get up here, all of a sudden, this little area of a sector of a circle is going to change. It's going to be hitting this arc that is r equal to 3. I'm off there a little bit, but you can get the idea. Then I'm going to change here again. So either I can find the area of this piece and multiply by whatever I have to, or I can find the area of this piece and multiply by whatever I have to for our symmetry. Okay? So once again, here's a point of consternation here. Right? And so what we have to do is find out where these two equations are simultaneous. And that's what we're going to be doing here in a second. So if I have two equations, R1 and R2, and I want to find out where they're simultaneous, I just set them equal to each other. Now this is not one of your easy solve ones that you did have in pre-calculus, so I had to go calculate this. Well, if you go to your polar graph and you do r equal to 3, you're going to find these 2 points. But in polar graph form on the calculator, you cannot find the intersection points. So this is kind of funky, but you do have to go to your rectangular coordinate system and you can find points of intersection. And so you should know how to do that. So on the calculator, you have to go over to rectangle to find the points of intersection. Can't do it in polar. Just so you know that. That's pretty important. So now let's set this up with our integral. So if I do take this, I do start at 0. Notice that when I start off, I'm going to be hitting the side of the pedal of the curve. So I'm going to go from 0 to 0.424. And in my r, and I'm going to have 1/2, I can put that up front. And then this is going to be 4 sine of 2 theta. So that's what I'm going to be running for to a quantity squared d theta. That goes all the way up to this point right here. Now I need to go from that point over. So I can either do this full pedal, which I'll probably do, or I can just do half of it and double it. I guess I'll just do half of it and double it. So then I'm going to add 1/2 from 0.424 to pi over 2, and I'm going to go, radius is now 3, quantity squared, d theta. That's the setup that I need. That would give me everything up to here. So everything in this region. So then you can go ahead and multiply that by whatever factor that I do need in order to get the rest of whatever we have. So if we do the full thing, we multiply by 8. If we do just one pedal, I'm just going to multiply by 2. Depends what they're asking for. Okay, so that's how you do the area when I have two curves. Yeah? So see where that laser shoots out, and you can figure out what goes on from there. All right, I hope this helps. Take care. Have a great day.